Okay, well, I guess we can get started, and if anyone else pops in, that's all right. And if they don't, that's just as all right. All right? Right. So, last time we met, we had introduced the concept of electrochemical cells, in particular voltaic cells, and we were learning kind of the ins and outs on how they're constructed and how we calculate the voltage they produce. So these are the kinds of cells that we use a spontaneous chemical reaction to create electricity, electrical energy. So I just want to make sure we pace this well, and I want to mostly focus today on just practicing that skill from last time. So let's reinforce it. Let's get this part down solid. And I want to kind of do some back and forth with you off of these problems, like these questions that are from that problem set thing. And then I thought it might be interesting also to look at some of the past AP problems in recent history that have appeared on the exam, so you get a sense of what we're doing and how it's reflected in the exam, like the form that you would see it in typically. So let's see how far we get with that today, and more next time is needed. So let's kind of review where we left off. Da, 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 da. Oopsie, I don't want that. Let me bring up a document. And if you recall, I believe we had only worked through one particular cell, and it was the one that looks something like this, where we took, and we're keeping all the concentrations at 1 molar solutions right now. Those are called standard cell potentials that we get, and later we're going to learn how changing the concentration affects that. But for now, if we grab, let's put the copper on this side. I think this is the one we built previously, just to kind of back into this whole lesson. And then I think we use zinc and zinc, and then we turn it on and we get a voltage and we kind of observe how things are moving around. So while that's running, sorry, my document's moving in the right direction here. Let's kind of lay out all the pieces that we learned about this last time. So the first thing we said obviously is the image of the cell and the layout, but at the molecular level, we can see at one end we have electrons being transferred in, and they are reducing ions to their metallic form. So this is the reduction side. You see that happening there. Those electrons are coming from this side, which is the oxidation side, where atoms in the metallic state are losing electrons, then dissolving into the solution. Meanwhile, for the entire system to work, we need the salt bridge connecting the two half cells so that ions can continue to flow and maintain a continuous flow of electricity. So representing all this, we showed several things. Number one, we can show it in that line notation, where remember we always have the anode is where the oxidation reaction happens. And in these voltaic cells, we said this is going to be the negative terminal of our cell. And then the cathode, we said, is always where the reduction reaction occurs. And in the voltaic cells, that's going to be the positive terminal, and you can see that here. This is the negative side is usually the black wire, and the positive is the red wire. And when we turn this, I got to start it over. Gosh, I'm not going to do it again. But anyway, you can see that we get the voltage to be positive when we do it the right way. So this is always true, and we have that mnemonic. An ox, like the animal, cat, red, or red cat, if you will, like the other animal, just to help you remember that pattern. And so to calculate the voltage, we said that we can find the voltage of a standard cell by taking the voltage of the reduction reaction minus the voltage of the oxidation reaction. They're really just reduction potentials, and they're the ones we look up on the table. So it might be easier to write it this way. We're going to take whatever is happening at the cathode and then subtract the value at the anode. So we have to go back and find those. So if I went into the table of values that we saw on that, oops, keep forgetting what class I'm in. Here we go. The standard reduction potentials table. When you're doing this on an exam, they're going to give you a truncated version of the ones you need. You know, it's not going to be like this giant table you have to keep looking through. But we're looking for, in this case, copper and zinc, right? So we have to be specific. This has copper, but it's the wrong one because this is showing it going from +2 to +1. We're looking for copper +2 going neutral here. So when we take this one, and I'm just going to copy them the way they are for the moment so we know how to use this properly. Again, this is largely review from last time, but I'm just doing this so that I can then give you a couple to try on your own and see if you can go through the whole process yourself. So we have this piece, and then the other one was zinc here. All right. Of course it does it like that. All right, just do it. Really? Oh my gosh, this is so annoying. Oh, well, let me do it that way. And still nothing. Okay then. I can do it. I can do it, I promise. Voila. Okay. So now, let's just make it look a little prettier. So remember, we said that these tables are always written in the form of reduction potentials. And so we know that in these reactions, they're not both going to be reduction. One's going to be oxidation. So one of these reactions is written backwards. Now, the way we know which is basically which has the higher reduction potential. So whichever one has the higher reduction potential, and by higher we just mean the more positive one, that's going to be the cathode. That's going to be, in that case, the one that's reduced. And so that's how we know. So when I'm looking at these two, 0.34 is bigger than negative 0.76. So this is going to be my cathode reaction, meaning this is going to be where the reduction happens. And this is going to be the anode where the oxidation happens. So now again, you see that this table of reduction potentials is set up the way it is, understanding that if we flip the equation around, in other words, if I turn these two equations around and showed them as oxidations, we could reinvent this table and it would now be an oxidation potentials table, but everything would flip sign. And we could make the arguments from the other point of view, but we don't. It's just simpler to keep it one reference frame and use it consistently. But it's absolutely true that we could write it the other way around and they would be oxidation potentials. And it's relative. Remember, we said the hydrogen ion reduction is like the reference point that everything is compared to. So it's like picking one kid in the class and saying, okay, you're the standard. We're all going to play tug of war or arm wrestle with you, and we're going to put ourselves in rank order compared to you. You're 0. Some are going to be above you. Some will be below you. And that's how it's done. So we can see that in this specific case that the math is really easy. It's subtraction. So since we know that this electrochemical cell, we're going to do the cathode minus the anode. So wait, the question is, if it's a negative number, it means it oxidizes? Not necessarily. It means it has a higher potential for oxidation than hydrogen does, right? Again, you have to think about it relative to what the reference point is. Because when we are comparing things, both of them can be negative, but one of them is more negative than the other, and so it's again relative. Now, like I said, the math here is quite simple because once we know what our cathode is, well, that's 0.34 volts relative to hydrogen. Then we're subtracting this negative 0.76, and that's how we got the 1.1 volts that we saw when we built the cell on the simulation. All right, I'll just throw it back in there. Let's just see it one more time. Ta-da, 1.1, just like we said. So now it's really about, can we lay out the proper mechanics of the cell? And one more representation we said was that line notation. So we could represent this entire cell system by, again, using what's called line notation, which is kind of a approximation of the picture. So we start with the anode side usually. Then we go toward the cathode side. And so we start with the electrode, which is the piece of metal that's the conducting piece inside the solution. So in our case, the anode is the zinc reaction and the solid is the zinc metal. So we have the zinc as a solid. Then we use a vertical line to represent a change in state or phase, meaning like if it's a solid in contact with a solution, this dividing line tells me we're changing state of matter. So here's the solid. It's in a solution of zinc ions. So that's the anode. That's a half cell, and it has a half reaction associated with it. Then we use the double vertical line to represent the salt bridge, which remember is that connector that allows the current, the electricity to flow all the way through the circuit. Remember, if this little bridge isn't here, the ions can't get across and the whole system kind of piles up charge on opposite sides and then stops. So here's the one half cell, the anode side. Then on the cathode side, we go the other way. Now we're starting from the solution, which is in this case copper, which is being reduced to metallic copper, the solid. So again, the line notation is just kind of a way to simply draw the cell picture in a little more compact form, versus if we actually wanted to sketch the cell, this can be kind of presented in a more 3D way by saying, okay, we have a container with some solution. We have the one electrode in here, which is again our anode. We have the zinc solution in here, and again I'm just showing the net ionic form. I'm not worrying about the spectators right now. Then we have the second container of the other half reaction. We have the other electrode in here, which is the copper. We have our bridge, our salt bridge, in which is typically some non-reactive concentrated ionic compound dissolved in water, like potassium nitrate is often used. And then we have something for the electricity to go through, whether it's a voltmeter or whatever. Could be a light bulb if you like. But the key point now is, can we label the parts? Do you see how all the pieces fit together and how the electricity flows? So again, just labeling everything. This is the anode, and it's the negative cell, or the negative electrode in the cell. This is the cathode, which is the positive terminal. Oh, I forgot my ions down here, sorry. Put put those in. These are the copper ions. We should understand the flow of electrons. So in this case, the electrons were always going to flow from the anode to the cathode, right? They're going to leave this side and flow into here because it's the electrons, remember, that are reducing the metal on this cathode side. They're coming in and they're being absorbed by these metal ions, whereas they're being produced by the zinc dissolving and releasing electrons. And so the electrons are flowing in this direction. Meanwhile, we have the ions in the solution migrating. So in the salt bridge, potassium ions, which are positive, are going to be drawn in this direction. Because if negative charge is flowing in here, positive charge has to flow in the same direction to balance it. Otherwise, again, it would build up one kind of charge into the beaker. Meanwhile, where the negative charge is leaving from, the ions in the salt bridge, the negative ones have to go in to replace them. So you should be able to discuss the flow of the ions in the salt bridge as well. Now, do you remember what we call negative ions in a solution? This fancy name for negative ion versus positive ion? Remember anion and cation? Now you should be able to see why they're called that. Look at what's going on here. Oh, good question. The salt bridge is porous, so it doesn't let the solutions mix in a gross way. Think about like a ball of cotton here, but it does let ions to cross the gap. So ions can flow, but the liquids are maintained as separate things. But look at what this is going on here. The positive ions are called cations because they're attracted to the cathode. That's where the word cation comes from. And the anions are moving toward the anode. Amazing. It all makes sense. So that's where cations and anions come from. Right? Okay. So there's no cats. Oh, haha, get it. All right. The final thing that we would want to know about what's going on in here is related again to the chemistry of the reaction. Since this is where the oxidation is occurring, and this is where the reduction is occurring, if I asked you to write the reactions, the half reactions, this is what I'd expect you to write. So the half where'd that random green line come from? Go away. I would expect that you would write something like this. You'd say, oh, okay, this is good. So the actual reaction itself, this is the zinc becoming zinc and 2 electrons. The reduction reaction, now be careful, is the copper ions gaining electrons to become copper, and the net or the overall reaction would be the sum of those two. So the overall reaction that this cell is using to produce electricity is just the sum of these two half reactions. So this is a relatively simple one because there's not too much going on. The electrons already kind of work out because it's 2 in and 2 out per atom. So if you just kind of cross off, whoops, if you cross off the right things, cross off the electrons here, and then you can see the net ionic equation for this reaction in the cell is copper ions plus zinc metal produce zinc ions plus copper metal. And then you should be able to comment on what's happening to the electrodes themselves. So the cathode is going to gain mass. And the reason for that is we're plating it with ions from the solution being neutralized onto its surface. So they're going to get fatter. But the anode is going to lose mass because in this case, the metal is dissolving as a result of the ions forming and releasing the electrons to the circuit. And so that kind of takes us back to where we got to last time. Is there anything you want me to clarify? Because this really pretty much tells you everything you need to know about this basic type of cell.
I
Yeah,
wanted to ask about like in the work. I tried some of the problems from the problem set, and I just don't understand which what is it called? Like which reduction to choose from the table based on their like wording and the phrasing in the problems.
that's perfect. That's where we should go next then.
Oh,
So
okay.
let's pick one. So go ahead, tell me which one you looked at that might follow that, and then I'll go through it with you.
Okay, I tried the second one, and even the first one I wasn't totally sure.
Okay.
But yeah, the second one was a little confusing to me.
Let me open that. Okay, so when you say the first and the second one, do you mean
As in B.
ah?
Not
So
wait, no. Go up, go up. The where it says is the iron. No,
wait.
no, no. Go
Oh,
down.
I'm sorry. Oh, this one?
1B, yeah.
Oh, 1B.
A1B.
A1B, got it. That's a good question because there might be more than one possible answer the way they're offering it. So let's take a look. So to answer a question like this, we have to look at a table of potential reduction potentials and look for what's going on. So let me just line things up here so we can look at both at the same time. Okay, so if we want to talk about these, we have to find them somewhere. And I'm going to look at all the ones that may be relevant because it's just asking, can it? So it kind of depends. So let's look for anything related to iodide. So if I start at the beginning, looking for I minus, oh, that's kind of, but now that's IO3. No, that's not it. That's too complicated. Oh, what's this? So this is showing its reduction, but it's showing, okay, what did I just do here? I just turned on some feature that I don't want. It's highlighting everything. I hope I didn't just do that for the whole thing. Let's see. Try that again. Sorry. My gosh, it's so funny how this computer gets slow on a Friday. It's like a student. um, just kidding. You're so mean. Uh, I think I'm funnier in person. Okay, anyway, so we're going to take I2 plus 2I minus goes to 2I, or 2 electrons goes to 2I minus. And the reduction potential for this one, I'm not going to put the little red, I'm just going to assume we know, is 0.54. Okay, so let's just put that on the side. Now we're looking for iron 3. Well, here's one. So here's something that shows that iron 3, oops, got off my pad here, and 1 electron produces iron 2. And that reduction potential is 0.77. These are all in volts, the electrical unit of potential difference. Let's see if there's any other irons that might be of interest. Nothing. Oh, here's one. Here's an iron plus 3. And I'm going through all of these for a reason, just because I want to really address your question deeply by showing you that we can look at more than one possibility here. Since the question was put in a pretty vague way. But now you'll see this reduction potential is negative 0.036. And then there's one more. Oh no, we don't need another one because that's iron 2. Those are the iron 3s, I think. Yeah, that's it. So we have these 3 that we have to consider. Now these are all reduction potentials. So they're comparing how well one is reduced compared to another. We want to oxidize the iodine, right? So we want something that's easier to be reduced because we want it to be reduced by the iodine. In other words, we want this to happen. We want the iodide ions to lose the electrons, right? That's oxidation, isn't it? So right now, if you compared this one and this one, this iron has the higher reduction potential, right? So this one wants to be reduced more than iodine does. So if we were to set this up kind of in a cell, what I imagine would happen is that this is the one that would get reduced because it's got the higher reduction potential. This one would get oxidized. Now I'm going to write it the other way around. Don't get confused. Because it has the lower reduction potential. I'm going to keep this as a positive number for now, just for the sake of doing the math. And so the difference between this is going to give us a positive value, which means this reaction is spontaneous. This will happen if we just let it. Now, the net ionic equation, you'll notice we're not balanced right now. And we told you last time that if you double the entire equation, it does not affect the voltage. This stays the same. It does not affect the voltage. So now if we add this up, this reaction did I put my electrons on the, wait a second. Sorry, I messed up something. This is +1 makes, why did I reverse this one? Did I reverse them both? This is reduction, this is, I put it backwards. Sorry about that. I wanted to put it, I reversed it again. I meant to leave it in the oxidized form. So we can show the electrons now cancel, and the net equation is this, plus 2 iodides makes 2 iron 2s plus I2. So this is showing exactly what you were asking. If we use this one, then we can in fact cause the oxidation. If we tried doing it with this reaction, it wouldn't work, right? Because this is not higher in the ability to reduce than the iodine is. So that's kind of what you have to consider. That make sense?
Yeah, thank you. I was just like looking at all these options, like which one do I choose? But okay, so I should, if it's phrased that vaguely, like I should consider all the possibilities.
Yeah, and I don't expect you'd have more than a couple. And if even if you
Mhm.
did, like just to kind of give you a reference frame from which to speak to this, if we look at like an old AP question, um, you'll notice they're just giving you what you need, or they might be giving you a short list. And so now you have only a few to choose from. You know, it's not like you have to look through 30 things, just so you can see how that looks. Okay. Um, shall we try building an entire cell? Like go through the whole project. And when I try, I mean you guys do it, and then we'll check. So I don't remember if we did this one together last time. We might have, but I don't think it's a problem to do it again. I doubt. You know what? Actually, yeah. Let's actually. I'm going to pull both of these because they both have things I like, and they're both important examples. So what I did here, this whole pile, and I'll leave this as an example on the side. can you, with the resources in front of you, do with these problems? Whoopsie. Ah. Sorry, I'm trying to make it all fit so you can see everything you need to at once. So A and B, and we'll put some space. See if we can get them both in one. Okay, so go a little bit prettier. Go through the whole process of figuring out the cell, label everything like I labeled here. Just pretty much mimic this process for both of these. But I'm going to tell you one important difference. Remember, and I know this I said pretty quick last time, that sometimes the electrode is obvious because the reactive component is a solid and it's the actual piece of metal that's in the cell. But in cases where it's solutions only, you have to use an inert metal or a carbon graphite. So typically I would just say always use platinum for the electrodes when that's the case. In other words, when you're building your cell, there's going to be a chunk of platinum inside the beaker. And then there's going to be multiple ions within that same beaker. So that's the only thing that's a little bit weirder, okay? But that's why this is a good example, because it brings that kind of problem up. So I'm going to give you guys some minutes here to work on this, and then just ask me questions as you're going if you're not sure what to do. All right? A question has appeared. Oh, I didn't know if you didn't have that open. I can pop that open for you. I'm running out of screens. Sorry, I don't know how much I can fit of everything on here, so you might have to open some of this up on your own. Okay, I can fit that. Here's the questions, and I can leave up my model for now if that's easier. I don't know what you need to be looking at most, so you tell me. Oy vey, I went to the wrong side. Ugh. I hate it when this happens. There you go. There's a catch, what you need. Oh, that table? It's in, if you go to my website, like online, not on Canvas yet, because this isn't in Canvas, but like on my normal website, and go to AP Chem and Unit 13, the standard reduction potentials and everything else is there. Actually, what I could do is just put this site link into this calendar. it in here. Whoops. Oh yeah, we're not going to do that yet. Keep that there. Um, Sorry. I'll move things back in just a sec. Just get this on there. Where's the... All right, that should take you directly to this page where all those little shortcuts are. Oops. As long as you can stay, I'm just gonna, wrap up these problems probably and see where we're at. But I don't think it should take much longer than that. Miriam, can you clarify your question? So it's showing you that it's copper and copper plus 2, so you're looking for that specific reduction potential. And yeah. You guys want to finish the first one and go over it before we do the second one? Just to make sure you look good? Okay, so that's, I think, the plan. Yeah, try to sketch the cell. Kind of follow. I mean, they all look about the same. It's just you're replacing the parts. You guys need more time? We can start. Oops. All right. So let's see what we did here. Throw me a bone here. What you got? Like, tell me where you started and what you did. Just so I'll kind of reproduce it on the page here for us. Oops. Wrong document. Anyone? Bueller. What'd you do first?
Um, I first found the potentials or whatever from the table based on like the changes that they gave me. So like from the silver solid to the +1 ion, and then same thing for the copper. And then I compared their potentials to figure out which one was the anode or the cathode.
So let's put the reduction reactions, both, and their potentials were what for each?
For silver, I got 0.8, and for copper, it was 0.34.
Okay. So what did, oops, 0.34. What did you conclude from these two reduction potentials?
That silver was being reduced, so it's the cathode, and that copper is being oxidized, so it's the anode.
Good. Now there's no particular order we have to go in. We could get the net equation here, we can whatever. So it doesn't matter to me what order we go in. So go ahead and tell me what you want another piece of this. What can we get from this now that we know these parts? Like if I asked you for the cell potential, what would you do? Put this little zero here.
I'd subtract 0.34 from 0.8 to
That's
get
it.
the. Yeah.
Just the bigger one minus the smaller one, basically. And that's what, 0.46? Okay. So then, at this point, we can represent either, I'm just trying to remember the order I did it before, not that it matters, but did I do the line notation next? I don't remember. Was that, or what did you do next? You tell me. I'd rather hear from you than me.
Maybe we could do the net ionic equation.
That's good. So the reduction is going to stay in the same order. But what do we have to change about it to make this work? Can I just leave it like this? We've got to match the electrons, right? So I got to double this line. And the oxidation one has to be flipped because it's going to go the other way. Oops. The electrons cancel. And then our net equation is silver ions and copper make silver and copper ion. So far, so good?
Quick question.
Sure.
How come you can only flip the second one?
Well, because what the numbers tell us is which one is more reducible, like which one wants to be reduced more, right? So we've already claimed that this is the one that's going to be reduced. That means it has to go this way. And if this one's reduced, the other one has to be oxidized. So it's going in the other direction. Now, when we do non-spontaneous electrochemical cells, which are called electrolytic cells, can we drive the reaction backwards? Yes. But notice the kind of symmetry here. If the reaction happens naturally, it generates electricity. But if we want to drive it backwards, we have to pump electricity in to reverse the reaction. And so we're going to see that in the second half of this unit, that right now we're looking at the spontaneous cells, the ones that we can use the chemistry to generate the electricity. But we're going to learn we can also use electricity to push a chemical reaction against its will. Like pushing a ball up a hill, you do work, you provide energy to do that, but the ball naturally rolls down. So Zaina, did I answer your question? Or?
Yeah.
Okay. All right, where do we go from here? What do you want to do next? Which piece of the pie? Don't matter to me.
The line notation?
Sure, let's put it together. So what should we start with?
The copper.
Let's see, the copper. in the solid form, line, then what comes?
The copper with the +2.
Yeah, that's the copper in solution. Salt bridge, then
Silver with the plus.
silver ions. I'm going to use the balancing coefficient. I don't know that we need to, but just for the sake of balancing, I guess. And then,
The silver solid.
perfect. And it's understood that the left half is the anode, where the oxidation happens, and the right half is the cathode, where the reduction happens, et cetera, et cetera.
I have a question.
Yeah.
With the salt bridge, what kind of what would it have in there? And, like, would it stay the same like the last one?
Yeah, we can always use the same stuff in the salt bridge. It doesn't really matter as long as it's not something that's going to be reactive in the system. So it's usually going to be something that's really hard to oxidize or reduce. Like that's why if I use potassium and nitrate, both of these are like the potassium ions are going to be really hard to reduce, and the nitrate ions are going to be really hard to oxidize because the nitrogen's already superoxidized. And so we don't expect these to really interfere with the reactions that we're doing. Now it's not shown in the line notation, but this was just to answer your question. Yeah. All right, I think all we have left is the picture then, right? And hopefully it makes sense that once you've kind of drawn the line notation, you can just translate that right into the picture. So I expect you drew something like this. I'll draw it in a slightly different form this time just for fun. Watch this. Different kind of salt bridge. Same idea. Solution, solution, semi-permeable membrane. We'll put the KNO3 in here. Again, same idea. Just a different way to connect the two sides. Instead of across, we're going through. What's the difference? There's other kinds of ways you can do this too. You can do one kind of semi-permeable cup in another cup and put one solution here and one here. So there's different formats you might see this in. It doesn't really matter. In the end, you just need a bridge, something that connects. And then we can put our copper here, our silver here. I'm assuming this is what you did, but if I'm wrong, just let me know. I'll put 2 silvers in here just for the sake of balance. Again, I don't think you have to worry about that, but just to be more explicit. Now, what's more important to me, though, is the flow. So we know we're going through this circuit. Which way do the electrons go? Give me a general direction. So our anode. This is the oxidation. This is the
right?
They go this way, right?
Yeah.
Yeah. So that's the flow of the electrons. Again, it's technically 2 electrons net per cycle of the reaction. And then in terms of the ions, again, wherever the negative charge is flowing away from, new negative charge has to flow toward to replace it. And where the negative charge is flowing into, positive ions have to come in to keep the system neutral. And so that gives you the drift. Or if you just remember anion to anode, cation to cathode, I guess that helps too. And then this other side, just to kind of finish this off, this will be the cathode, which is where our reduction we said happens, which is our positive terminal on the battery, or on the, if we're measuring it on a meter or whatever. Okay, is that getting any better? Like more clear each time? Let's just try this last one, because it's a little harder because of the weirdness of it. Let me put on a new page. That's weird, a little piece of my beaker broke off. So try this one. It's essentially the same kind of problem. It's just weird because you have to use platinum electrodes and you have multiple ions instead of a solid and an ion. But otherwise, it's exactly the same problem. So you have to find these on the chart, the relevant ones that are related to see who's the oxidation, who's the reduction, all that. Okay? Give it a whirl. And if you're not sure about something, just like I said, keep posting those questions up and I'll answer them. I could probably put the chart up. You don't need the model anymore because you have it written down probably at least twice at this point. Where did I put here? Oops, that's the one I want. Make sure they're both up there. Okay, that one's there. Yeah, they're both there. Hint, they're both on the left side. Zoom in and help you out a little bit here. Yeah, I think I got them both on the screen right now. We should probably start. Oops. we should probably start looking at it just to make sure we're on the right track because time is getting there. Oops. Oh, bye, Kristen. So let's take a look. So let's make sure we pick the right reactions. So to me, it looks like it's this one and the last one. So that's good. So if we pull those ones out, we would have, where is it? Permanganate plus 8 hydrogen. This starts to look familiar. These look like things we did first semester with redox balancing. Manganese 2 in water. And then that's got a potential of 1.51 volts. And the other one I'm just going to copy, iron plus electron makes iron. 0.77 volts. I think that's all we need from there so we can move into this mode. Which one is going to be reduced? First or second?
First.
Yeah, so this is our reduction again. This is our oxidation. So again, we can kind of zip through a few of these things pretty quick. We know that E cell, the potential of the cell we build with these systems, is just going to be 1.5 minus 0.77, which is what, point something 4, 0.74? Yeah, I think that's right. Does that look good? Okay, so that's our chemical potential. The net equation on this one looks a little more complicated. It's not too bad. That's a nice thing here is that the half reaction's already balanced for you. Right? Remember, first semester when we did this, we had to go through the whole process of balancing half reactions. Here they're giving you balanced half reactions. You just have to combine them by focusing on the electrons. Okay, no problem, Zeno. So all I have to do here now is going to have to switch this around into its oxidation form. And then I have to, obviously, if I look at the 5 electrons, I have to multiply this by 5. And then we should have our balanced net ionic equation. Man, if we had learned this first semester, we could have saved so much time instead of having to balance all those half reactions. You know you loved it. Sorry, I'm getting sloppy at the end here. All right, so there's our balanced equation. Now, here, to build this cell is, like we said, a little quirkier because of the fact that neither side has a natural electrode. So we'll just slide some platinum in there. But let's do this in the line notation first. So I'd start with solid platinum, one line. Since the anode side is our iron, we're going to have both of them in there, and I'm going to do it in the oxidation direction, meaning I'll put the +2 first, comma, the +3, so I can show the oxidation process as I read it left to right. I didn't put the little aqueous symbols, whatever. It's implied. Salt bridge. Then, again, the order that it's being reduced in, it's the permanganate, comma, the manganese 2 ions, because that's the direction it's being reduced. Line, and then another platinum electrode. There's your line notation. I'm not going to bother with the coefficients. Okay, and then finally, to construct our cell, go back to the traditional form here. I can't draw so good. Okay, so we'll shove some platinum in on this side. We'll shove some platinum in on this side. This is our oxidation side, so we have a combination of the two ions in this solution. And so if you can picture what's going on, the iron 2s are becoming iron 3s and giving up electrons. That's what's happening in this oxidation. We have our path here. Our electrons are being lost at this end and going in this direction. In this case, it looks like we have a total of 5 electrons per reaction cycle. And then on the opposite side, we have a combination of permanganate ions as well as manganese ions, as well as, now we got to be careful here. Notice that this has an acidic medium. So technically that should be included, right? Those hydrogen ions are in there as well. I don't remember now if did I include it in the, I think I did. So I believe we should include those in the line notation as well, because they're part of that system. And then finally, just to kind of lay out exactly what's going on here in terms of the ions. Again, we keep getting the same pattern. In the salt bridge, which has, let's keep assuming potassium nitrate, the nitrates are going toward the anode, our negative terminal. The potassiums are going toward our cathode, our positive terminal. And so you just see that one minor adjustment is the fact that we have to throw the platinum in and we have multiple ions in solution. But otherwise it works the same way. How's that looking so far? Good with the cells? All right. So here's what I would ask you to do for next time. Instead of just looking at more problem set stuff, I just threw it on this kind of pseudo syllabus here. Maybe just try to do this free response 2018, all except for B3. So it's one free response question that's related to what we just learned. But the third part talks about delta G, which we haven't learned yet. That's going to be in the thermo piece that we're moving toward in regular class. And just try that and see how it looks to you by next time. And we'll go over it and then we'll see where we're at. And we'll advance the ball a little bit more next time. Yes, as far as the salt bridge, it could always be the same. But like I said, be aware that in some questions, they're going to make it look funky. So look at this one. Right? This is looking a little different, but it's the same idea. It's just a funky one that I remember because I was still teaching it when this one came out, and I'm like, a lot of kids are like, what was that? I'm like, it's just an electrochemical cell. It doesn't matter that they made it look different. It has the same principles. You know, that's why I'm trying to show different versions of things when I can. But anywho, just looking at any more pictures. Nah, not really. That's it for today. Have a lovely weekend, and as always, I fully appreciate the extra time you're willing to put in. Thank you.
Thank you. Have a
Thank
great
you.
weekend.
You too. Thank y'all.